So in this video we're going to look at reflections of toolbox functions over the x and the y axes. The basic idea is that if we have a toolbox function f of x and we create a new function g of x from f by negating the input variables, then the graph of g is just the graph of f reflected over the y-axis. And similarly, vertical reflections or reflections over the x-axis, if we have a toolbox function f of x and we create a new function from f of x by negating f of x, then the graph of g, the new function, is just the graph of f reflected over the x-axis. So we're going to start off looking at this with the simplest possible function. So here I have a function f of x that's just given by 2 points. This is the point 2, 3. This is the point -2, -1. So this is my graph of f of x. And f of x is just the two ordered pairs, 2 and 3, -2 and -1. So first I could look at the function g of x that I build from negating the input variables. Notice that this negation is on the input variable. So when I take the 2 and the 3, this negative on the x just says put a negative sign in front of the input variable. And then I have the other point, -2, -1, and this negation says to make g of x put a negative sign in front of that input variable. If we do that, we wind up with -2 and 3, and here we get an ordered pair that is a double negation, so that makes that a +2 and a -1. And if we plot those points, plot the point -2 and 3, and the point 2 and -1, what we see is that this point is just this one reflected over the y-axis, and this point is just this point reflected over the y-axis. So putting the negation on the input variable reflected our function over the y-axis. And then we could play the same game. We could make a new function h of x, which we make by negating f of x. So if we take those same two ordered pairs that we started with, f of x was 2 and 3, and the other ordered pair was -2, -1. But now this says put the negation on the output. Remember, ordered pairs come in inputs and outputs, and f of x represents output. So this negation right here is on the output. So I come into the ordered pair, I negate the output. If I negate a negative, I get a positive, so I wind up with 2, -3, 2, -3, which is just this point reflected over the x-axis, and then we wind up with the point -2, +1, which is just this point reflected over the x-axis. So now we can do the same thing, but we can do it with the toolbox function. So I say, hey, this looks like a toolbox function. Which one does it look like? It looks like the square root function. F of x equals the square root of x. And then we play the same game that we've been playing, where we find just a few lattice points. There's 3 right there. This is the point 0, 0. This is the point 1, 1. And this is the point input 4, output 2. So if you first consider making a new function g of x by doing f of the opposite of x, this says negate the input variables, negate the x's. So if I negate 0, I still get 0. But if I negate 1, I get a negative 1. And that gives me negative 1, 1. And if I negate the input variable here, I get a negative 4, which brings me over here, negative 4, and up 2. The negation was on the input variable, so it had no negations on the input variable, so it has no impact on the outputs. And then you hand draw your square root function up through those 3 points. That's really bad though, isn't it? Try one more time to do a better job. Oh, come on, get rid of that eraser. Maybe if I swing in from this direction, swing in. Oh, it still messed it up. So then the other function, make a new function h of x that's equal to the opposite of f of x. This one says put the negations on the outputs. So if we put the negations on the outputs, if we negate the 0, we are still stuck at the origin. We negate the output of negative 1, we'll have 1, negative 1 as a point on the graph. If we negate the output, the 2, we get 4 and negative 2. And there's our 3 lattice points, and then we try to draw. Whoops, I hit the eraser on accident. We try to draw. Oh my word. That's why I did this in GeoGebra before. That's horrible. There's my lattice point. And you draw the line through those points. So again, GeoGebra does a much nicer job, but I think you get the general picture. You want something that's a smooth curve that looks like this, that's passing through those points, and usually you're going to erase it until you get it, or use software to do it. One last try. Yeah, still horrible. Alright, so here we have a parabola. So the function family that we're working with here is f of x equals x squared. That's the toolbox function. Grab yourself a couple of nice lattice points. There's a bunch of them on this. So we've got the origin. We've got the point 1, 1. We've got the point 2, 4, negative 2, 4, and negative 1, 1. So the key is to recognize that if we were to graph f of negative x, which just negates the input variables, because the parabola has even symmetry, we won't see any change. So there really isn't any point in doing f of negative x other than to bring up the point that because we have even symmetry, the graph will be the same. In fact, what's the test for even symmetry? Even symmetry, the test was, does f of x equal f of negative x? And if it does, you have even symmetry. A parabola has even symmetry. These two graphs are going to look identical. Now make the graph g of x. That looks like the opposite of f of x. That means negate the output variables. So we're negating the 1 and the 4. If we negate 0, we just get 0, so the origin stays where it's at. But this point gets reflected over the x-axis. This point, this 4 will become negative 4 and get reflected over the x-axis. Net 1 gets reflected to negative 1 over the x-axis, and this 4 gets reflected to negative 4 over the x-axis. And in general, I think I expect people to label the points. This is going to be 2, negative 4. This is going to be negative 1, and this is negative 2, negative 4. And again, like before, we tried to draw the smooth curve, picking those points up. And this is why I like GeoGebra, because my artistic skills really leave a lot to be desired. Parabola opening, supposed to be a parabola opening downwards. Oh well, better luck next time.